Hello and welcome back to Educator.com and welcome back to Biochemistry. So the last lesson we started a review of some general chemical principles that are going to lay the foundation for the work that we do in biochemistry. So for the next couple of lessons we're going to continue that. Today we're going to be discussing dilution and osmotic pressure. The notion of osmosis is profoundly important in biological systems. The cell is a semi-permeable membrane, and the relationship that the cell has with its surroundings outside the cell, inside the cell, is all based on the difference in concentration. So osmosis is huge in biological systems. Okay, let's just go ahead and jump in. So let's begin with dilution. So you all know from experience what dilution is. Basically, you are changing a given concentration by the addition of solvent. So if you have some solution and it has a certain concentration, if you add more solvent to it, the concentration of the solute is going to diminish. Because remember, like molarity is moles of solute over liters of solution, right? Moles over liters. If the number of moles of solute stays the same in there, but all of a sudden I up the liters of solution by adding more solvent to it, well, this is a fraction. As the denominator increases, the concentration decreases. So that's what dilution is. Okay. So once again, you want to change a given concentration by the addition of solvent. You're trying to dilute the solute. Let's go ahead and do an example. And this is a very, very important example because it's something that all of you are going to do at one time or another if you haven't already. So a student is given a stock solution. Let me erase this actually. Is given a stock solution of hydrochloric acid, which is 11.8 molar. How can he prepare 500 milliliters of a 1.5 molar HCl solution from this stock? So basically he has this solution which is 11.8 molarity, but what he needs is he needs to create 500 milliliters of a 1.5 molar. So how is he going to do this? Well, let's think about what he's going to do. So basically what he needs to do is he needs to put in a certain amount of stock solution of a given molarity, and he needs to dilute that by adding water, bringing it up to 500 milliliters, and then making sure that that 500 milliliters is 1.5 molar. So the question becomes, how much of the stock is he actually going to pull out of the stock solution to put into this beaker, and then on top of that add the water to bring it to 500 mils to turn this into a 1.5 molar solution. That's what we're doing here. Okay, so the basic dilution equation is as follows. The basic dilution equation, it says that the initial molarity of something times its initial volume is equal to its final molarity times its final volume, also written as M1V1 equals M2. Let's make this a little clear. So M1 V1 equals M2 V2. So this M is molarity, not mass. Very, very important. So the molarity times the volume that we start off with, in other words, of the stock solution, once we've diluted it, the final molarity, the final volume. So this is the equation that we want to work with. So again, we're concerned with, let me go to red, we want to know how much stock do we have to pull from the stock solution to dilute that up to 500 milliliters. That's what we're trying to do. Okay, well, let's take a look at what it is that we actually have. So we know so we need this, 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 and this. And of course, with any equation that has 4 different parameters, you can be given any of the other 3 in order to find the 4th. So the problem itself is going to dictate which parameter that you're actually looking for. In this case, let's see what it is that we have, and then we'll find out what parameter we need. Well, we know what the final volume is going to be. So the final volume, that one equals 500 milliliters, or 0.5 liters, depending on which units you're going to use, as long as the units are consistent. So we have the final volume, and we also have the final molarity. That's going to be, we're looking for a solution which is 1.5 molar. So our final, I'm just going to make my M's the way that I am comfortable doing it here. How's that? Our final molarity is going to be 1.5 molar. Okay, well, what's our initial molarity? Well, our initial molarity, we're using a stock solution, and the initial molarity is 11.8 molar. So that's going to be 11.8. So the only thing that we're missing is the initial volume. In other words, I need to find how much of the stock solution I'm going to dilute to 500 milliliters. I'm going to put in a certain amount of stock solution. That's this, my initial volume of my stock, and on top of that, I'm going to add water to bring that final volume to 500. So that's what I do. Well, this is nice and easy. Very basic equation. We'll just go ahead and put it in. So we have initial volume times initial molarity, which is 11.8, equal, you know what I'm going to do? I'm actually going to use the units here, and because I want you to see what cancels and what doesn't. So we have V sub I times 11.8 moles per liter. That's the initial volume, and molarity is equal to the final volume, which is going to be 0.500 liters, because we're dealing with moles per liter, so the units have to match so that they can cancel. And the final volume, that's this one, the molarity is 1.5 moles per liter. I just switch them around. Here I have M first and V second. Here I have V first and M second. So sorry about that. I hope that doesn't confuse you. So that's it. Now let me go ahead and solve for my initial volume. So V sub I is going to equal 0.0636 liters, or 63.6 milliliters. So 63.6 milliliters is the amount of stock solution that I'm going to pull, and I'm going to add that to a beaker, and then I'm going to bring that volume up. So let me go ahead and write out the procedure. So take 63.6 milliliters of stock solution, stock HCl, and pour into a volumetric flask. I'm sorry, a 500 milliliter volumetric flask, because we're creating, now we want to be as precise as possible. I mean, you can use a beaker if you want, but again, you're trying to create a solution, so you want to use a 500 milliliter volumetric flask. Those are flasks that are specifically calibrated to create a very, very accurate volume. 500 mils, 250 mils, 1,000 mils, 50 mils, and they have a certain mark on them to tell you where to stop adding water. At that point, you're exactly where you should be. So you pour this 63.6 milliliters of stock into a 500 milliliter volumetric. Flask. Then add solvent. Add water until the mark, which is 500 mils. And then just mix thoroughly, and there you go. That's it. The dilution equation. The molarity, the initial molarity times the initial volume equals the final molarity times the final volume. There are 4 parameters here. In order to find the one that you want, you have to have the other 3. That's it. Okay? Now, the idea behind this equation, M1V, let me write the equation again. Let me go back to black here. So the idea behind this, M1V1 equals M2V2, the idea behind this is that when you're diluting something, when you're adding solvent to something, you're not changing the solute amount. So the amount of solute, whether it's floating around in 100 milliliters of solution or floating around in 1,000 milliliters of solution, it's still the same amount that's floating around in solution. There just happens to be a hell of a lot more solvent now in which it can float around. So the number of moles of solute actually stays the same. That's what this equation is based on. So let me write this as moles per liter times liter equals moles per liter times liter. Well, liter cancels, leaving you the initial number of moles is going to equal the final number of moles. That's the whole idea here. That's what this equation is based on. The amount of solute doesn't change. The moles of solute floating around are the same. The only thing that changes is the volume. So given this, I'm going to go ahead and do this problem again in an alternate way, just for the sake of doing it in an alternate way. I personally do it this second way. I don't use the M1V1 equation, but I know a lot of kids actually prefer an equation to work with. But I think about it like this, in terms of keeping the amount of solute constant. So